A finished tire hides its own complexity so well that most people never question it. You see black rubber, some grooves, a brand name pressed into the side. What you do not see is a layered structure built with millimeter precision, engineered to survive forces that would tear apart simpler materials in minutes. At highway speed, a tire flexes and recovers its shape around 15 times every second. It heats up, cools down, grips, slips, compresses, and rebounds. And it does all of that because of decisions made long before it ever touches a road. The process begins with raw materials, but even calling them raw is misleading. Each one has already been refined to meet strict specifications. Natural rubber arrives in dense blocks, typically weighing between 30 and 40 kilograms. These blocks are cut from sheets that were once liquid latex, tapped from rubber trees and chemically treated to stabilize them. The rubber is elastic but not yet suitable for a tire. On its own, it would be too soft and too sensitive to temperature changes. Synthetic rubber complements this. Produced from petroleum derivatives, it can be tailored for specific performance traits. Styrene butadiene rubber is common in tread compounds because it resists abrasion. Butadiene rubber is added for flexibility, especially in cold conditions where natural rubber stiffens. The ratio between natural and synthetic rubber is adjusted depending on the type of tire. A summer tire may lean more heavily on synthetic blends for heat resistance. A winter tire shifts toward flexibility at low temperatures. Carbon black is one of the most visually striking materials in the process. It is a fine jet black powder that clings to surfaces and disperses easily into the rubber. Its role is structural. At a microscopic level, carbon black particles interact with polymer chains in the rubber, reinforcing them. This increases tensile strength and resistance to wear. It also helps conduct heat away from the tread, reducing the risk of overheating. Without carbon black, tires would wear out in a fraction of their current lifespan. There is also processing oils that adjust how easily the rubber flows during shaping, resins that influence grip, and small but critical additives like zinc oxide and stearic acid. Sulfur is included in controlled amounts because it will later form crosslinks between polymer chains during curing. Accelerators and activators are added to control the speed and efficiency of that reaction. Every ingredient is weighed with precision. Industrial scales measure batched down to small fractions of a kilogram, even when total batch sizes reach 200 kilograms or more. The formulation is not just about getting the right ingredients, but getting them in the right sequence. Mixing takes place in large internal mixers. These machines are enclosed, heavy-duty systems designed to handle high loads. Inside, two rotors spin in opposite directions, pulling the material through tight clearances. The rubber and additives are subjected to intense shear forces. Friction generates heat, and external heating systems maintain the temperature within a target range, often between 150 and 170 degrees Celsius. The order of addition matters. Rubber goes in first, followed by reinforcing fillers like carbon black. Oils and softeners are added to improve flow. Sulfur and accelerators are introduced later, because early exposure to high heat could trigger premature cross-linking. That would make the rubber difficult to process in later stages. As the mixture develops, its consistency changes. It starts as a collection of separate materials and becomes a uniform cohesive mass. Sensors monitor temperature, torque, and mixing time. If the torque rises too high, it indicates the mixture is becoming too stiff. If the temperature climbs too quickly, it risks damaging the material. Operators adjust parameters in real time to maintain consistency from batch to batch. Once mixing is complete, the rubber is discharged while still hot and fed into a series of rollers. These rollers flatten it into sheets of controlled thickness. The sheets are cooled, often using water or air systems, and then cut into manageable sections. At this stage, the material is called compound, and different compounds are produced for different parts of the tire. The next phase shapes these compounds into functional components. Extrusion is one of the primary methods. In an extruder, rubber is pushed forward by a rotating screw inside a heated barrel. As it moves, it is compressed and heated further, becoming more fluid. At the end of the barrel, it passes through a die that defines its shape. For the tread, the die produces a wide, thick strip with a precise profile. The surface is smooth because the final pattern will be formed later. The dimensions must be exact because any variation will affect the final tire's balance and performance. Sidewalls are extruded separately using a different compound. This rubber must resist environmental factors like ozone, ultraviolet light, and moisture. It also needs to flex repeatedly without cracking. The thickness of the sidewall is carefully controlled as it influences both ride comfort and durability. Calendaring is used to create reinforced layers. In this process, rubber is pressed into thin sheets and combined with fabric or steel cords. Large rollers squeeze the materials together under pressure, embedding the cords within the rubber. The spacing and alignment of these cords are critical. They determine how the tire handles stress and how it maintains its shape under load. Textile cords, often made from polyester or nylon, form the body plies. These plies provide flexibility and strength. Steel cords form the belts that sit beneath the tread. They are arranged at specific angles to control how the tread deforms during contact with the road. This affects grip, wear, and fuel efficiency. Beads are constructed by winding steel wire into loops. These loops are coated in rubber and shaped to precise dimensions. The bead must fit tightly against the wheel rim, creating an airtight seal. It also anchors the tire in place, preventing it from slipping under acceleration or braking. With all components prepared, the process moves to assembly. Tire building machines are designed to layer these components in a specific sequence. A rotating drum serves as the base. The inner liner is applied first, forming the airtight core of the tire. This layer is thin but essential, often made from butyl rubber because of its low permeability. Body plies are added next, wrapping around the drum and extending beyond the edges. Beads are positioned at these edges, and the plies are folded over them, locking them in place. This creates the basic structure of the tire. Sidewalls are applied over the plies, followed by the steel belts. The belts are aligned carefully to ensure uniform strength across the tread area. Finally, the tread strip is placed on top, completing the layered structure. At this stage, the tire is still cylindrical. To achieve its final shape, the drum expands or an internal bladder inflates, pushing the layers outward. This gives the tire its rounded profile and ensures that all components are properly seated against each other. The result is a green tire. It looks like a finished tire, but it is soft and lacks strength. The layers are held together by the natural stickiness of the rubber, but there are no chemical bonds yet. The tire can be deformed easily, and it must be handled with care as it moves to the next stage. Curing is where the transformation becomes permanent. The green tire is placed into a mold that contains the negative of the final result. The mold is heated and an internal bladder inflates to press the tire outward. Temperatures typically range from 170 to 200 degrees Celsius, and pressure ensures that the rubber flows into every detail of the mold. This is where the tread pattern forms. Grooves, channels, and small cuts called sipes are pressed into the rubber. These features are not just cosmetic. They control how water is displaced, how the tire grips the road, and how it wears over time. At the same time, vulcanization occurs, creating a network that gives the rubber its elasticity and strength. The density of these crosslinks is carefully controlled. It affects hardness, flexibility, and resistance to heat. Curing time varies depending on the size and type of tire. A standard passenger tire may take around 10 to 15 minutes. Larger tires, such as those used on trucks, require longer times to ensure that heat penetrates evenly through the structure. When the tire is removed from the mold, it has its final shape and properties. It is firm, resilient, and capable of handling stress. However, the process is not complete until it has been inspected. Inspection combines automated systems and human oversight. Uniformity machines spin the tire and measure variations in force and geometry. Even small imbalances can affect how a tire performs on a vehicle. Sensors detect deviations in stiffness, thickness, and shape. X-ray systems provide a view inside the tire. They reveal the alignment of steel belts and cords, ensuring there are no gaps, overlaps, or foreign objects trapped inside. Only tires that meet strict standards are approved. Those that do not are rejected or reprocessed. This level of quality control is necessary because a tire failure can have serious consequences. After inspection, finishing steps are carried out. Excess rubber, known as flash, is trimmed away. Surface markings are checked for clarity. Identification codes, including manufacturing date and plant location, are verified. These codes allow tires to be traced back through the production process if needed. The finished tire is then ready for distribution. it will be mounted on a wheel, inflated, and eventually put into service. From that point on, it will experience conditions that test every aspect of its design. The final product may look simple, but it is the result of controlled chemical reactions, precise mechanical shaping, and rigorous testing. It is built to handle forces that are constantly changing, from the smooth rotation of highway driving to the sudden impact of a pothole.